I'm back. Get it? Yep. Back. Okay, let's make an orbital filling diagram. I mean, who wouldn't want to make one? That's nothing else, but I have nothing else better to do on a Sunday afternoon, Easter Sunday afternoon, wearing my Sunday best. Let's make an orbital filling diagram. I'll show you why I want to make an orbital filling diagram when we make the diagram. Hopefully you'll go, wow, now I can see why this might be important in chemistry. An orbital filling diagram is going to show where the electrons live, hang out around the nucleus of an atom. So let's see what we'll do is we will pick a relatively simple atom, carbon. Carbon. You've heard of carbon. It's where you store your automobiles. You store them in a car bin. So I always, when I make an orbital filling diagram, like to draw in at the bottom a little half circle with an end meeting the nucleus. You don't have to do that, but that's just me. Just me. Just me. All right. Then what we're going to do is we're going to draw the first energy level represented by the number 1, because the first energy level is the one that's closest to the nucleus, and then 2, 3, 4, 5, 6. It makes sense. So energy level 1 is down here close to the nucleus. And energy level 1, as we remember from the last video, only has one sublevel, and it's an S sublevel. So I like to put 1S to represent energy level 1 and the sublevel that it has, an S sublevel. Now, an S sublevel can hold, remember? Do you remember from the first video? An S sublevel can hold 2 electrons. And remember what an orbital is? It's a place where 2 electrons could hang out. So therefore, we represent the 1s sublevel with 1 orbital, and that 1 orbital is where those 2 electrons that could be in the first energy level, and they can only hold 2, that's where those 2 electrons could be placed. All right? And they'll want to be placed there, because what happens is if you're an electron, remember the charge of an electron, you're a negative. Protons hang out in the nucleus. Those are positive. And those positive electrons, the positive protons in the nucleus, like those negative electrons. So if you're an electron, you want to be hunkered down as close to that proton mass down here in the nucleus as you can be, because that's where you're attracted to. You want to be down there. So the electrons will want to go in here if given an opportunity to do so. Now, there's not a lot of room down there, so we can only hold 2, and everybody else is going to find somewhere else to hang out. So that would be energy level 2 would be next. Energy level 2 has 2 sublevels. See, remember 2 sublevels. Remember what they are? S, always have an S, and P would be next. P next. So I like to draw an S and a P like that, and I like the little lines to kind of show that they're connected to energy level 2. A sublevel S has 1 orbital. That's always true, but a sublevel is 1 orbital. A P sublevel, remember how many electrons that can hold? Remember? 6. Therefore, let's see, each orbital can hold 2 electrons, 6 electrons, 2 divided by 6, 3. That would be 3 orbitals possible. 3 orbitals, that's possible, 3 orbitals in the P sublevel. Now remember in the beginning of the last video where we did 2n squared, we could figure out how many electrons each energy level could hold, 2n squared. And we figured out for the second energy level, we put a 2 in for n, and square 2 is 4 times 2, 2n squared equals 8. We get a total of 8 electrons. Check it out. Energy level 2 with its 2 sublevels, this could hold 2, 3, 4, 5, 6, 7, 8. 8 electrons. We have room for those 8 electrons, and we've drawn that out. All right, now, let's see. I wanted to start out with a simple element, carbon. Carbon is element number 6. And what that means is element number 6. Remember the element numbers, the atomic numbers mean how many protons you have. And it also means how many electrons you have, unless you're an ion. We're talking about a carbon atom, which means you're going to have 6 protons. To balance that off, 6 electrons. So this is an orbital filling diagram for electrons. So we're going to show where the electrons hang out. The 6 electrons, where would they hang out? Now we know that electrons want to be close to the nucleus. Positive, negative. So those first 2 out of the 6 electrons are going to be hanging out down here in this room of the S sublevel in the first level. So I will draw the one arrow up. Remember, arrows represent our electrons, and they're opposite because they're spinning in different directions. Again, you don't need to know that. It's too much for what we need to know. But they do. So what we're going to do next is say, all right, I've got 2 electrons accounted for. I need 6 altogether. Let's see, 6 minus 2, 4. 4. I have 4 more electrons I have to account for. Where are the next 2 going to go? I just gave you the hint right here. Why? Because it's closest to the nucleus. Anything wants to be close to the nucleus. If they can do it, they don't want to be hanging out up here. They want to hang down here close to what they like, where they want to be. So that next 2 electrons go here and here. All right, now we have 2 more electrons to account for. Where would those hang out? Okay, let's see. I am going to draw in one here, and you might be tempted to put the next one here just like we have been doing. You would be so wrong. Remember, these electrons are negatives, and a negative and negative, they don't like each other. They do not want to be hanging out in the same orbital, same room, if there's another orbital or room available. They'll take that room. Thank you very much. I want to hang out with him. He smells. He never showers. I want my own room. So that electron will do that. It'll hang out in a sense. That 6th electron will go not here, but here. All right. In fact, if we look at our sheet, we have several words down here at the bottom. Pauli exclusion principle, Hund's rule, and the Aufbau principle. Actually, we're showing the Aufbau principle. Aufbau is a German word for meaning building up, and that's exactly what we're doing. You build your orbital filling diagrams from the bottom up, because that's where electrons want to be, close to the nucleus. So we are doing the old Aufbau thing. Okay, that's what I always say to one of my soccer players when they're standing on the soccer ball. Hey, you, Aufbau! This one here, Hund's rule. Hund's rule is what we're demonstrating now. I'm actually doing Hund's rule now. But you've heard of Hun before. You know, he was a Mongolian guy. No, that was Genghis Khan. Hun, Attila the Hun. Oh, conquer Rome, Attila the Hun. No, that's Attila the Hun. Sorry, no, I got my history screwed up. Hey, Hun, never mind, moving on. Hund's rule says that we don't put electrons in the same orbital if there's room in another orbital. So I'm going to put that other electron over here. Now you might be saying, which way should I have it spinning? Up or down? Up. We up until we have to go down. Up. So I'm going to put that next electron here. It doesn't want to hang out with this electron. There's an empty room. It'll take it. Because remember, they don't like each other. Now you might be saying to yourself, what about these down here? You know, they don't like each other either. So maybe this one wants to jump up. Oh, no, jump up. You see, you just said jump up. They don't want to jump up. They'd rather be close and be next to each other, even though they hate each other, than getting away. Because of the closeness to the nucleus is the most important thing, these electrons. Okay, it overpowers the desire to be away from each other. So these are going to stay down here. But there is something interesting that does happen to carbon. So maybe it's going to sound at first like I'm contradicting what I just said, but what carbon will do is this electron here will move into this spot here. Wait a minute, you just said that they don't want to jump up. They would rather stay down together than jump up. I know that's what I just said, but this is actually special. Carbon is actually special. It's interesting, I chose this one, but when I was in the middle of doing it, I realized that carbon does something called hybridize. Hybridization, and that means that the carbon electron here will move to this spot up here. And let me just show you what's kind of neat about that when that happens. Is you now have, and this is actually what will happen in these 2 sublevels that actually kind of go together and make one big sublevel. And I want to get into that now this week. I just want to keep things kind of simple, but this is carbon's unique in that it would allow this to happen. Everything else, they want to stay down close and stay together, like I was saying earlier. But this does form an ability for carbon to form 4 bonds. Carbon wants to form 4 bonds. And this is why we start getting into why are these orbital diagrams important because they show where the bonding is going to happen and why it happens. So carbon has a spot here, a spot here, a spot here, and a spot here, that there's room for these electrons to come in to those unfilled orbitals. And that's why we get bonding. We're going to find out this in 2 weeks when we get into bonding, and why things would want to fill in these spots. We're going to draw Lewis structures and whatnot. But these 4 spots, for now, here's what we need to know. If we have an open spot, that's a bonding spot. That means carbon wants to form 4 bonds. And the simplest hydrocarbon, you can see that, CH4, means it's carbon with 1, 2, 3, 4 hydrogens. And the reason those 4 hydrogens go into those spots is because spots are open and they're called bonding areas, bonding spots. So these orbital filling diagrams show why bonding is going to happen. Okay, that's carbon. Now, if I were to ask you, like on an exam next week, draw me carbon, then if you drew me this, great, you would not be wrong. If you drew me this, also not wrong. It follows the off-ball principle and the Hund's rule, and it doesn't show hybridizing, which is fine because not everything hybridizes. It's a rare thing. So if you were to show me that, then that's fine for carbon. Okay, fine. Let's do one more. Let's try a different one. Let's try element number 13. Aluminum. Aluminum, number 13 has 13 protons, 13 electrons. We have to draw 13 arrows to represent where those electrons are hanging out. Okay, so here we go. Off ball, bottom up. 1s. 2 has an S and a P, sublevel. Energy level 3, that has an S, a P, and a D, SP and a D. So we have an S, P, and a D. Remember how many electrons can be held in a D sublevel? 10. 5 orbitals. 5 dashed lines. There's my setup, and I think that probably is going to be enough room to accommodate the 13 electrons that I have to put in here. I think I'm going to be okay with this. Let's see. So let's start putting the electrons in. Well, make them a different colors. Make them blue. Okay, here we go. Off ball, bottom up. 1, 2, 3, 4. Now I'm just going to show you Hund's rule. 5, 6, 7, because that's how they would fill. Unless they have to be doubled up, they will fill up singly first. That's Hund's rule. Okay, 1, 2, 3, 4, 5, 6, 7. I need 13. I have 6 more. 6 more arrows. I am going to have to fill these spots in because these would fill next. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 1 more electron. We'll put that electron up here. No. Bottom up, fill bottom up. We're putting it right here. Now, is it possible for that electron to move up to a different energy level? Is that possible? Sure it is. That's absolutely possible. It's called the excited state. Ground state is when everything is down low as possible that they can get close to the nuclei. If things get nailed by some kind of an energy source, like a photon or heat energy, like you're going to be doing a lab on this today, so pay attention. Then they can jump up to a higher level. But they don't want to be up there. They won't be up there very long. They don't like it up there. It's like if you're afraid of heights, climbing to the top of a ladder. You know, how long are you going to want to be up there? Not very long. They want to get down as soon as possible. Get back where you're comfy. So you're going to want to go boom, back down to the ground state. But you can move up into higher energy levels, the excited state. But you will come back down. Okay, that is aluminum. Uno más. Let's do scandium. Scandium. Scandium is, we all remember number 21 on the periodic table. And 21 means 21 even in college, okay? Remember that. Or even at a frat party. 21 is 21. 21 electrons. Here we go. Okay, scandium. 1s, 2s, and 2p, 3s, 3p, 3d, Now, Scandium 21, I might have to use another energy level to accommodate 21 electrons. So I'm going to draw in the 4th energy level. I'm going to put it right here. You ready for this? We know the 4s would be the first sub-level in that 4th energy level. Watch where I put it. What? What did you just do? You're rocking my world. Melting. Yes, the 4s sub-level fills before the 3D does. How am I supposed to know that? I'll show you. There's a way of knowing how to do it. It's called reading the periodic table, and you'll be able to figure this out. But just for now, so we can get this video done, let's just trust me. The 4s fills before the 3D does. I know it's weird. It's called overlapping, and this overlapping can become annoying. But for now, let's just get this done. 21 electrons. Here we go. 1, 2, 3, 4, 5, 6, 7. Off-bawing and Hund's ruling. And actually, I'm doing Pauli exclusion principling too. That's the other one on there. Pauli exclusion principle basically is saying that you cannot have 2 electrons in the same orbital spinning the same direction. They have to go opposite spins, which is what we're showing. So we're showing that Pauli exclusion principle as well. It's not quite what it says, but that's what it means. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and finally 21. The 21st electron goes into the 3D sublevel, which fills after the 4s. That's confusing. Wait, it gets better. As you go higher and higher in elements, imagine if we were doing this for element number 92, uranium. Not my uranium, your uranium. 92 electrons. 92 electrons. This is only 21 electrons. If I want to accommodate 92 electrons, I'm going to need a much bigger board. Probably have to go to the 2nd floor to accommodate those in an orbital filling diagram. Orbital filling diagrams become cumbersome to draw as we get larger and larger atoms for 2 reasons. 1, it's just room. 2, this overlapping becomes, whoa, so much more overlapping as you get into these higher energy levels. And how are you supposed to know that? That is coming in the next video. And we have a better way of representing where electrons are hanging out. Well, I won't say a better way, but a different way that's a little quicker than orbital filling diagrams, called electron configurations. I'll leave you on the edge of your seats, just waiting. You can't wait. Oh, I'm gonna go get myself a little drink of water and some milk and cookies. Yeah, milk, cookies, and water. And I'm gonna have a snack, and when I come back, I'm gonna be pumped. Wow.